Okay, so the next speaker of the session is Vicente González Bosca, and he's going to talk about simulating realistic effects in MDI-QKD. The stage is yours.
Hi everybody, my name is Vicente and I work here at CSIC, right across the street. And today I want to talk about simulating realistic effects in MDI-QKD. And as Victor said, the goal of QKD is to share a secret key between two parties, usually called Alice and Bob. And for that, they are going to encode these bits, which will be strings of zeros and ones, in quantum states of light. They can use polarization to encode these bits. And for example, if they use the rectilinear basis, they can agree to have the horizontal state to be 0 and the vertical state to be 1. And of course, they could choose any other basis they want, for example, the diagonal basis. And this would be like the kind of like scheme of a BB84 protocol. But today I want to focus on measurement device independent protocol, which was invented by one of the collaborators of Victor, Marcos Curti. And it's a little bit more complex because you don't have an emitter and a receptor. But in this case, both Alice and Bob become emitters, and they send their states to an untrusted node called Charlie. And Charlie will perform some kind of measurements, like he could detect photons there or there, any possible combination. And then he will announce his results. With these results, and according to these rules that you can see in the paper, Alice and Bob will be able to distill a secret key. And for simulating this protocol, our goal here is to calculate the detection probabilities. We would like to compute the probabilities of detecting photons here, or these coincident clicks. So with this complexity, of course, comes some advantages. The first one is that Charlie could be in total control of a third party, and you would still get a safe protocol. So you eliminate all the side channel attacks to the measurement units. It's also very suitable for kind of a network architecture because Charlie could be a common node for many units in this network. And then in principle, you could double the maximum distance achievable by a sender-receptor protocol. And to understand the basics of this protocol and why it's safe, I would like to show you some very simple calculations. So imagine Alice and Bob send the horizontal state. This horizontal state could be written in terms of the creation operator applied to the vacuum state. And I do this way because once we get to the beam splitter, I can relate the creation operators at the output of the beam splitter in terms of the operators at the entrance via this matrix equation we see here. So once we do this, we can calculate the output state. So we apply the operators and I've expanded them here. And if you see this last term here in a 50-50 beam splitter where R and T are equal, this term would cancel out. And this cancellation, it's called a Hongo-Mandel effect or Hongo-Mandel interference. And if you look at the output wave function, what you see is that you have a 50% chance to measure the two photons in either arm of the beam splitter, but you won't get coincidence detection. That is, you can't measure one photon in one arm and then the other photon in the other arm. So this state here, it's an unentangled state. So you could perform a Bell state measurement, and that's what we do with the extra stuff here at Charlie, the polarizing beam splitters, and then the detectors. To model the polarizing beam splitters, it's easy. You just need to consider the horizontal and vertical modes of the polarization separately. And then to model the detectors or the probability of detecting, you say it's proportional to the square norm of the annihilator operator applied to the state. We can write everything in terms of annihilator operator, and that simplifies the calculations a lot. So this is the equation that relates that. But then we are, free to go to compute these probabilities. Something worth noting here is that for this Hongo model interference to happen, we need Alice and Bob's state to be identical. That means they must be indistinguishable here at the beam splitter. And in particular, that implies that we need to have the same frequency, and they have to arrive there at the same time. And in practice, this is very difficult. For example, like single photon sources, which could be one of these things we use to emit photons, are irregular. They're unreliable in the firing times. So we wouldn't know when our photon is emitted, so we have some difficulties on getting there at the same time. Then they also have very poor, for these applications, their wavelength is not very good, and they're expensive and slow. So in practice, many people use coherent states that can be achieved using amplitude modulators and attenuators that are cheap, fast, and the precision or the temporal precision and the wavelength of your light depends on your electronics and the laser you choose to modulate. So these coherent states mathematically are defined as the eigenfunctions of the annihilator operator, and the key parameter here is this alpha here, the eigenvalue, which defines the mean number of photons per pulse. So with the amplitude modulator, you will create a pulse, and then you will attenuate to the level of individual photons with an attenuator, and then you send that state. But when creating your pulse, you have to choose a width for that pulse. And if, for example, the frequencies of your lasers, remember, they have to be equal, but in practice, they will be a little bit far apart. If they're very far apart, you will want to make your pulse very thin in time, because then in frequency, it will be wider, and you will have some overlap, and you will produce interference. And all this can be introduced in the calculations considering this state, which is a tensor product over all the frequency modes, and weighting this, this alpha with the shape of the pulse. But on the other hand, if you don't have very temporal accuracy, you will want to make your pulse wider in time. So again, you have some overlap in space and time. So there's a trade-off between frequency and time to design the width of your pulse. That's something like you would like to optimize to produce the maximum interference. So this delay of getting there can also be modeled by introducing this exponential here. And with all this in mind, we can calculate the detection probabilities, as the probability of detection will be proportional. This S here is the efficiency of the detector. And then you need to integrate over all the frequencies of the square norm of the annihilator operator applied to the state. Since in MDI-QKD, we're interested in coincidence probabilities, in coincident clicks in the detectors, we compute the probabilities of detecting a detector IJ and detector KL of the setup. And we were able to, reduce these probabilities to a nice formula. Here it's very condensed, where we can identify 4 terms. The first one, B, this B here, it's the baseline term. That it's there because we're dealing with coherent states and will always be there. Then we have these R's here, R here and R there, that stand for random. We'll see why. And then this I here, it's the interference term. The big phi here, kind of like if we use Gaussian pulses, you can actually compute the formula for this phi. Will tell you how good your interference is. So, in the ideal case, when you have same frequencies and you get your pulses at the same time in the beam splitter, You will have your probability. It's your proportional to the baseline term plus the interference term. And in the worst case scenario where you don't have interference, you will get probability equal or proportional to baseline term plus random term. And for those of you interested in QKD, with this formula here, you could compute your quantum bit error rate and the yields and gains of the decoy state method that Victor mentioned. And with that, you could optimize the decoy intensities and probabilities. Also, this is the optimal width of the pulse to get maximum interference. And we ran some simulations and saw that with optimized parameters, you get to a farther distance, which is nice. That's it. I'd like to thank my colleagues that helped me do these calculations. And some final remarks are that there's many things that you can introduce, and we have introduced in the probabilities, like or the simulation, like detector efficiency, dark counts, solar count, polarization mismatch. But we have limited time, so if you want to ask about that, or you can ask now or after in the coffee break. And that's it.
Well, is it working? Sorry. Thank you very much, Vicente. Is there any question? I had one. Could you elaborate a bit more on the Hongo-Mandel interference and why that term cancels out?
Yeah.
Like
so
physics of it.
Yeah, basically. Sorry, I went a little bit fast. So you're expanding. You apply your creation operators here to the vacuum state. With this formula, you relate them. So here, what I'm doing is expanding them, just like via this relationship. And in a 50-50 beam splitter, that I forgot to mention, this beam splitter is 50-50. So the parameters, the reflectivity and transmittivity of the beam splitter are the same. This term here cancels out because T equal to R. So you get that, and then you apply this to the state, and you get this wave function. That's it. But if your beam splitter is not perfect, you will have a residual term here that will affect your interference.
Okay, thank you. Any other question? If not, thank Vicente again, and move to the next one.